So what if you can't make the bases the same? So finally, that's what we use logs for. So here are the steps that we're going to be taking. We're going to make sure the base is by itself. It has no coefficient other than 1. We'll take the log, common log or natural log of each side. It's handy to use the natural log instead of the common log, although the answer is going to be the same no matter what base you use. Use the power law rule to, quote, bring down the powers, and then you solve for the variable. Because the problem has always been that the variable that we want to solve for is in the exponent, and it's the power rule of logarithms that allows us to bring that variable down out of the exponent, where then we can solve. Let's take a look at some examples. Solve 5 to the x plus 2 equals 4 to the x. 5 to the x plus 2 is equal to 4 to the x. So the first thing we do is we make sure the bases are by themselves. There's no coefficient. There's nothing else going on that we need to get rid of, so fine. We're going to take the log, either the natural log or the common log of each side. And again, at first glance, if you haven't done this before, you might think, well, how does that help? Well, we have something called the power rule. And the power rule says that if you're taking the log of something being raised to a power, it's the same as that power multiplied by the log. So we can now bring down these powers, and we have x plus 2 times natural log of 5 is equal to x times the natural log of 4. So let's take a look. What we can do now is we can either change these values into decimal approximations and keep going. Sometimes it's nice to wait and do that later, because every time you round off, you lose a little bit of precision. So what I'm going to do is I'm going to divide both sides by natural log of 5, divide by natural log of 5. And so now we have x plus 2 is equal to x times the natural log of 4 divided by the natural log of 5. So now what I'm going to do is I'm going to turn this into a decimal approximation and continue solving. So the natural log of 4 divided by the natural log of 5 can be approximated by 0.8614. So 0.8614x is equal to x plus 2. We'll subtract 0.8614x from each side. So that tells us that 0.1386x, because remember this is 1x, is equal to, and let's go ahead and subtract 2 from each side, so that would give us this. And then the finishing touch, to get x by itself, we would simply take negative 2 and divide it by 0.1386, giving us a value of x being approximately equal to negative 14.43. Okay, so the idea is get the base by itself, take the log of each side. Any log will do. I use the natural log, and we'll see later on why it's handy to use the natural log. That allows you to bring down the powers and then just keep on solving. Here, let's try another. 2 to the x is equal to 3 to the x plus 1. So we'll take the natural log of each side. That allows us to bring down the powers. So that tells us that x times the natural log of 2 is equal to x plus 1 times the natural log of 3. So what I'm going to do now is I'm going to divide both sides by natural log of 3. And again, there's many different ways you could go from here. These are just numbers that you could enter into your calculator if you'd rather. These will cancel. Natural log of 2 divided by the natural log of 3 is approximately equal to 0.6309. So we have 0.6309x is equal to 1x plus 1. We'll subtract 0.6309x from each side. So that will give us 0.3691x. And we'll also subtract 1 from each side, giving us negative 1 equal to that. Dividing by the decimal will give us our answer. And so if we do that, we find out that x is approximately equal to negative 2.709. Let's take a look at another. Solve e to the x plus 4 plus 6 is equal to 52. So here's an example of one where we have to do this first step. Make sure that the base is by itself. So here's our base being raised to a power, and on one side of the equation, it also has a positive 6 with it. So we're going to start by subtracting 6 from each side. That gives us e to the x plus 4 is equal to 46. Now we'll take the log of each side. And again, the reason we do that is because the power rule allows us to bring this out of the exponent. So what we'll have is x plus 4 times the natural log of e is equal to the natural log of 46. Now, this is why I like to use the natural log, because at this point, the natural log of e is equal to 1. So the natural log of e is equal to 1, and 1 times anything is itself, so we don't have to worry about that. So if I had the common log of e, that's not equal to 1. I couldn't just cross it out. But using natural logs, whenever I see the natural log of e, I can just remember, oh, that's just equal to 1. I don't have to carry it around anymore. So I have x plus 4 is equal to the natural log of 46. We'll just subtract 4 from each side. So x is equal to the natural log of 46 minus 4. And that is equal to negative 7.1714. Okay, we'll do one more example. Solve 4 times e to the 2x plus 1 is equal to 20. And again, here is our base right here. Our base is e. Let's start off by getting rid of the 4. So we're going to divide both sides by 4, giving us e to the 2x plus 1 is equal to 5. Now we'll take the natural log of each side, allowing us to bring down the power. So we have 2x plus 1 times the natural log of e is equal to the natural log of 5. Again, one of the reasons we like to use the natural log is because whenever we come across natural log of e, we can remember that's equal to 1, and 1 being multiplied by any value doesn't change the value of that other thing. So we have here, then, that 2x plus 1 is equal to the natural log of 5. And to solve for x, we would subtract 1 and then divide by 2. So let me enter that into my calculator, and you should practice entering this into your calculator as well, because you want to make sure that you are doing the order of operations correctly. This comes out to be about 0.3047. Now, let's talk about what would have happened had we not remembered to divide both sides by 4 first. If you had started off by taking 4e to the 2x plus 1 is equal to 20, and then taking the natural log of each side, you would be in trouble because you would be tempted to take this power and bring it down, and that would be a big mistake. Why? Because the power is not being applied to the 4, it's only being applied to the base e. And so this would be a wrong move that would lead you to the wrong answer. That's why it's really important that before you take the log of both sides of the equation, that you make sure that your base is isolated by itself. Otherwise, you could run into this trouble. Okay? So that's what you do if the bases are not the same. So I'm going to leave you with this one to try. Solve 2 to the x is equal to 5 to the 2x minus 1. Notice that these bases are isolated, so it's all right to take the log of each side, bring the powers down, and go ahead and solve.